Today we want to talk about motion, particularly things moving versus not moving. Now, one way we can tell if something is moving compared to an object that's not moving is with what's called a reference point. And what better, more important reference point could there be ever in history than the lighthouse, right? Lighthouses are made to be, they're purpose built as reference points, right? And so if you're on an object, let's say a boat that purposely does not do very well at staying still, right? Well, a reference point, somewhere where you can tell where you're at, well, that's a great example of something that might be very helpful for you. So it just compares where your location is compared to something that's, well, not in motion, something that's firm, that's fixed in place and everything. So lighthouses, they were put in places where sailors could know where they're at. And purposely built, they were often either made of different materials or painted different colors. So you could look on a handy dandy guide and see like, oh, I'm by this particular lighthouse. And that way you could find out where you were in the world, as a sailor, before a time where you could just look on your computer and it tells you within a few feet where you're at on the entire planet. Right? So that's what reference points do. They're just there to help you figure out where you're at. One great example of this is the stringless pendulum.
Hey everybody. Well, since we're talking about motion, well, what better way to do that than with the stringless pendulum? So just like a regular pendulum, a stringless pendulum, it has a bunch of weights involved in it, but instead of being attached with strings, well, we've just got a track that's angled on each side. It's kind of like a Newton's cradle, but without, the actual cradle part to it. So what these stringless pendulums do is they show transfer of energy, right? And so, as you would expect, if we ram one of the spheres in, well, basically the energy transfers through to, the next sphere, the next sphere, the next sphere, but then the last one, since it's, got nothing to stop it, well, that's why it kind of moves through, or the energy pulls through them. Now, we're talking about in motion, right? And clearly, right now, these spheres are not in motion. Again, we're not taking into account, obviously, the spin of Earth or the Milky Way or our galaxy traveling through the entire universe, because it's not relative to the experiment that we're doing right now. So compared to the things in this room, right? Clearly, the stringless pendulum, it's not moving right now compared to, let's say, the gas jets right here or the two rulers or something, that's close by to them. You can tell they're not moving. If I pull one back and let it go, well, then that one sphere is in motion. And as soon as it hits the other spheres, well, they become in motion. And then it sends, the next one moving, and the next one, and the next one, and the next, and the next, and the next. Yeah, and then, well, then the motion stops. And just like in a regular Newton's cradle, if I pull back two of the spheres and let them roll, well, then two on the other side come out, and then back and forth and back and forth and back and forth. And if I pull three of the spheres over on this side, hold on. There's motion, too much motion. Well, then when they come into contact, well, then three will split apart again. Anyway, here's a great example of no motion versus motion.
Another great example could be, let me show you this little video right here, right? This little video is from a wonderful movie a long, long time ago. And it starts out all nice and normal, right? Here you go. You have the, movie star of the time kind of singing around. It's just fantastic, this movie, right? Everything seems normal. Everything seems happy. Everybody's like, oh, what a great movie, right? You can imagine all these things, but wait, he's putting his feet on the furniture. That's not very nice. I mean, way back, and I don't know, in the 1940s or 50s maybe when this was made. But again, everything seems normal, right? Okay, we let the sting. Wait, he's back on the chair again. That's, back in the day, that just wasn't, you don't put your feet on the furniture. I mean, even today you don't put your feet on the furniture. But more feet on the furniture? See, not on the soft, cushy things. Wait, he's kicking the walls? Wait, he's getting a little uncouth here. Wait. No. How is that possible? Oh my goodness. Back in the 1950s, there would have been some little old lady that passed out in her chair right there. How is that possible? Wait, no. Don't do it. Don't you dare. Oh my goodness. Now you have to remember, this is made in a world before computer animation. right? So unlike some new Marvel movie or something like that, this kind of thing just didn't happen back in the day. I mean, how in the world is this humanly possible? Because everything is practical. And he clearly should be falling on the floor, right? I mean, how could this possibly be happening? Wait, what? Now he's on the other wall. So let's see the same scene again, but this time from a different perspective. This time, we've got our same star dancing around on the screen, and over here on this side, you can see what's happening in the movie screen, right? What's happening for people from the movie theater. But over on this side, you can see what actually practically was happening, right? It turns out it's not a matter of he gained superpowers. It's a matter of they built the entire set on, what's called a gimbal stage that they can roll the whole stage around, right? So he's not really dancing on the, floor or on the wall. It's that they made basically the ceiling turned into, the floor, right? All the furniture, right? All the furniture that's in the room, it's all being tied down or it's all connected in some way, right? Either it's literally bolted down or they have convenient magnets or something like that. The chandelier, it's not being held up by a chain or anything. It's a bar, right? Everything is attached really, really well to either the floor, the ceiling, the walls. And so that way, when it appears like he's just starting to dance on, the wall, it's just that the wall has become the floor, right? So it's all about perspective. It's all about where your viewpoint is, right? It's another handy dandy reason why you want to have a good reference point, right? Purposely in this scene, what they did is they turned what normally are reference points, things like furniture and, lighting fixtures and things like that, and they kind of fooled you around to thinking that they were where they're not. Even the curtains, if you look at the curtains, they're attached top and bottom, right? Just to kind of mess with your head. Oh, here they go again. So it's all about those reference points. So, think of things that are moving, right? They're, things, they're places where you would want a really good reference point. Right? So let's say if you're on a bus, right? Something that you might want to use if you're on a bus as a reference point, well, maybe like the sidewalk or something like that. Maybe, some of the trees that are around you. Those would all be good reference points. What would be a bad reference point is a car, right? Sometimes, especially like on a bus, maybe if you're just kind of sitting there, not really paying attention because you're on your phone or reading a book or something like that. If there's a car kind of parked beside you, let's say in traffic, all of a sudden, if the car takes off, you might think that you're moving when you're really not, right? That would be a bad reference point. Let's say if there was a ball rolling around on the floor, right? Well, a reference point might be the carpet itself or the other seats or something like that. Those would be good reference points that you could use. When you're playing pool, right? When you're playing pool, the pool table itself could be a reference point, or other spheres on the pool table that are not moving could also be reference points. If you're in an airplane, it can get really, really difficult, right? Have you ever seen an airplane way up high in the sky and it almost looks like it's not moving, even though it's moving really fast? It's because there are no reference points. But let's say if there was like a puffy cloud right beside it, well, then you could see like it goes whizzing past it really, really fast, right? Baby eating candy, right? What could be a reference point for that? Well, maybe the chair that the baby's in, or if it's in like a stroller or something like that. Those could all be good reference points. Again, kind of like the plane one, let's say a rocket ship traveling in space, right? If it's far away from everything, even though the rocket ship might be going at tremendous speeds, it could be really hard to see that because they're not reference points. So you would need like maybe, like an asteroid or a comet or something that you could use as a reference point. Now, the moon could be there, but if the moon's really far away, again, it might give you that it might be a bad reference point because it might make you think like, oh, it's not moving very fast at all, even though it might be moving thousands of miles an hour. Let's say, dandruff, right? Dandruff, right? Your shoulder could be the reference point for that one. Let's say if you drop something in your kitchen, right? It could be like the counters or the floor or the walls or something on there, right? Those could all be great reference points. Oh, there goes the pizza. Same thing. Here's the example in space, right? Here's a comet. This is actually a comet going through space. It's traveling at many thousands of miles an hour. But from our perspective, a comet, like if this was you looking at the comet, it would look like it's not moving at all, right? Unlike a shooting star that's really, really close. Remember, comets, I mean, they're so far away that they almost appear like they're not moving at all. Even a sunset, right? You might want to use the horizon could be the reference point for this, right? As the sun gets closer and closer and closer to that reference point, right? So all those are great examples of what you could use as a reference point.
The science spinner is an awesome tool talking about physics. They are purposely made of a clear, plasticky kind of material so that you can see that there is nothing inside of it. There are no magnets or weights or anything weird like that going on. And you can purchase them online, fairly cheaply because they're just a piece of plastic. Now the science spinner is for spinning, oddly enough, and it's a great way of just kind of like showing you a mystery of science, because here's the thing with the science spinner. If you spin it kind of counterclockwise, well, it does exactly what you would think it would, right? It kind of spins, and slowly the friction between the table and the actual bottom of the science spinner stops it. But here's the thing, if you spin it the other way, well, something quite different happens. If you spin it the other way, well, wait a minute, what in the world is that? It seems to not care about any of the laws of physics. It's like it just decides like, no, I'm going to spin my own way. What in the world, right? If you spin it this direction, it goes exactly the way you would think it would. But if you stop it and spin it the other way, it's like, no, I don't like spinning that way. I shall spin this way. Right? So that's the weird thing about the science spinner. Now, like I said, there are not magnets involved in this. There's not some kind of weird thing going on or anything like that. It turns out it's just pure physics, because if you look carefully at the shape of the science spinner, let me try to get it in there, right? It's not perfectly symmetrical, right? There's a weight that's higher on one side than the other side, and then same thing going, let me try to get it in there, the same thing going this way, right? More of the weight is on one side than the other. And so what happens is, well, gravity always wins, right? When you spin it, it doesn't always, when you spin it this direction, basically, the heavier mass is leaning forward, and so it likes that. But when you spin it the other way, the lighter end is up, and well, yeah, it doesn't like that, right? If, let's say, if this is the heavy end right here, if you're spinning it so that the heavy end is up, well, it's not going to like that. Gravity's going to push down on it, so it pulls it down. And as it pulls it down, because it's heavier on one side and on the other side, and on one end, both longitudinally and the other way, it kind of like gives it this rolling motion, and that's what sets it off on the path of wanting to spin the other direction. Okay, so that's the science spinner and what's going on with those. But they're just kind of a cool example of physics, right? It's kind of a cool example of, here we go, where is it? Cool example of, a mystery in physics that you can solve.